and I'd like to introduce Kaavya Sahay, who's from Yale, and she'll tell us about high threshold codes for neutral atom qubits with biased erasure errors.
Can people hear me? Yeah, thank you for the introduction. So today I'll be talking about this work, which is an error correction proposal in collaboration with Jeff Thompson's group at Princeton. So what we worked on here is we investigated this new form of structured noise, which we call biased erasure. And this is basically the dominant error channel experienced by the metastable is 171 ytterbium atomic qubit. And we analyze it in the context of error correction codes. And we see that this particular error model has extremely high thresholds to errors. So it has a threshold for the XZ surface code of 8% to gate errors. This is 8 times that of poly errors and double that of regular unbiased erasures. This means that if your gate infidelities arise from biased erasures, your logical information is preserved at much higher rates than if it is arising from biased erasures than from other forms of errors. We looked more closely at this error model and then derived a new kind of error correction protocol that we call hybrid fusion. This increased the threshold further to 10% and also reduced the qubit overhead we need for fault tolerance. So let's examine what biased erasure looks like in this qubit. Our qubit itself is encoded in this metastable level, and how we perform gates is we excite the one-state Rydberg level, as has been talked about several times today. And we have it interact with another atom, similarly in the Rydberg level, to enact a control phase gate. Now the dominant decay mechanism for this qubit is leakage from the Rydberg state. This leakage can occur back to the qubit subspace, or it can occur to a set of external states, including the ground state. It turns out that for this atom, decay to these external states dominates over the decay back to the qubit subspace. In fact, it is 98% of the total decay occurring. And what we can do is that we can take our control phase gate, apply a fluorescence pulse to non-destructively detect this leakage and creating a heralded erasure. There's one important point we need to focus on here, is that this leakage only ever occurred if your qubit started out in the one state. And so when you detect this leaked atom, you know that you have effectively measured your qubit in the Z basis. And so what we can do after this erasure detection is that we can reinitialize the qubit by replacing it with a fresh atom in the one state. So we have recovered the computational basis information, but we have lost all phase information associated with the initial qubit, thus creating at most a Z error on this qubit. So let's analyze the performance of this error model in an error correction code, the XZ surface code. So here we have a lattice of qubits. Each physical qubit is on the vertices, and each phase represents a stabilizer of the form XZZX, measured by control Z and control NOT gates. Now we've already seen what a Z error does to this code. It creates a -1 stabilizer outcome. And when we look at how that manifests for a control Z gate, we see that this Z error creates these two horizontal defect outcomes, which we can then pair together for error correction, leading to higher thresholds for biased noise, where Z noise dominates over X and Y errors. But our stabilizer measurement also uses a control NOT gate. And because our Rydberg atom does not have native control NOT gates, we have to implement this control NOT gate using a control Z conjugated with Haddon ones. This results in a biased erasure giving rise to a possible X error, destroying our noise bias. With this understanding, let's see if there's still any advantage for this error model with the XZ surface code. We take an error model where each gate experiences an error with a probability P. out of which an erasure fraction, RE, can be biased or unbiased erasures, and the rest are depolarizing polynoise. The results we get are as follows. So along the x-axis, you have the erasure fraction going from 0 to 1. On the y-axis, you have the error threshold. The blue curve represents unbiased erasures. The orange curve represents the native gate set with biased erasures. So when you start out at RE erasure fraction is equal to 0, you have the expected threshold of 1%. But then when you look at R is equal to 0.98, which is what happens physically with our qubit, you see that for unbiased erasures, we have a threshold of 4%, but with the native gate set of biased erasures, we have almost a doubling of the threshold to 8%. Now let's imagine that for this qubit, we could implement a bias preserving control NOT gate that did not take Z errors and turn them into X errors. In that case, we could get an even higher threshold of 9% and to preserve some good properties of the XZ surface code, which are right now not preserved. So this naturally leads into the question, is there a way to do better? Is there a way to perform error correction while preserving noise bias? And the answer, surprisingly, lies in the realm of photonic quantum computing, where entanglement is generated using multi-qubit measurements, specifically what we call the fusion or Bell measurements, which measures X, X, and ZZ on 2 qubits. Because we're using measurements to generate entanglement, we can no longer use a gate-based approach where we measure stabilizers again and again. We necessarily have to use a measurement-based approach to quantum computation. The measurement-based error correction protocol we're looking at today is called the XZ cluster state. Here I'm going to show a large cluster state, which is basically an entangled graph state. This looks complicated, but let me break it down. The dots in black are what we call X-type qubits, which initialize in plus. The open circles are what we call Z-type qubits that initialize in the 0 state. The lines between qubits represent local entanglement. What this state represents is basically a teleportation of the XZ surface code state. We take the XZ surface code on the left, and then we measure out the qubits in the respective bases. So we measure X qubits in the X basis and Z qubits in the Z basis to teleport this XZ surface code from the left of our cluster state all the way to the right of our cluster state in a bias-preserving manner. And what we see, similar to this XZ surface code, where Z errors created horizontal pairs of defects for error correction, is that in this XZ cluster state, Z errors also create these horizontal pairs of defects and give rise to high thresholds. So now we know that this cluster state can have high thresholds under bias noise. Our aim is to construct it in a manner such that the dominant errors during construction still give rise to only Z errors. And our protocol is as follows. First, we will probabilistically generate small entangled states, which we call resource states, and then we'll stitch them together using bias-preserving operations, such as control Z's and fusion measurements. The particular fusion circuit that we use in this protocol is shown here. We entangle 2 qubits with an answer using control Z gates and perform erasure detection. If no erasures are detected, then we measure out all the qubits in the X basis, getting the XX and the ZZ measurement outcomes we need for our fusion or Bell measurement. However, if a biased erasure occurs, we switch our basis of measurement to the Z basis and recover the ZZ measurement outcome at the expense of the XX measurement outcome. So any biased erasure erases the XX measurement outcome, and I'll shortly show you how this is the same as creating Z errors in our cluster state. Before that, what about these resource states? These resource states that we're interested in this construction are 8-body entangled states that we call the 8-ring, shown here, which is basically a GHZ state up to some Hadamard's. The circuit we use to generate it is shown as follows. There are a series of gates followed by a single erasure detection pulse. If no erasures are detected, then we have successfully generated our 8-ring resource states up to undetectable polys. However, if you have a biased erasure, then instead of running the risk of creating an X error, what you do is you reset the qubits and retry the circuit until you have a successfully generated resource state. Now that you've generated your resource states, let's pass them on to our fusion protocol. For simplicity, I'm only going to show these 2 central Z-type qubits and their immediate X-type neighbors. I then perform an XX measurement on these 2 Z-type qubits. This does 2 things. It firstly fuses these 2 Z-type qubits into a single virtual qubit with a 2-body ZZ logical operator. And secondly, it passes poly corrections onto two of the neighboring X-type qubits dependent on the measurement outcome. So, if I have a biased erasure, I already showed you that I lose the measurement outcome of XX. And if I don't know the XX measurement outcome, I don't know whether to apply I or Z to these neighboring X-type qubits, which looks like a correlated Z error in my cluster state. Let's use this in the construction of our cluster state. So I take my 8 rings, I place them in a single plane, and I fuse neighboring Z-type qubits using this XX measurement to create a single 2D planar array. I then put many of these planar arrays on top of each other, and I apply control phase gates between neighboring arrays to create my final cluster state. The last step involves measuring out the qubits in the respective bases for error correction and teleportation of my surface code state. This is simple for the X-type qubits, but if you remember, the Z-type qubits are secretly two-body Z qubits with a two-body ZZ operator. Measuring this and combining it with the initial XX measurement forms a complete fusion. And in fact, I don't need to do these at separate time steps. I can do them at the same time step because my ZZ measurement commutes with all other operations I'm using to build this cluster state. And so I can reorder my protocol to create a construction that uses the simple fusion circuit I used earlier. So now let's examine the performance of this protocol. I use the same error model that I did earlier, where each gate experiences an error with probability P, out of which a fraction can be erasures. We already showed you that the threshold error rate for zero erasure fraction is 1%, and for a gate-based approach is 8%. With this new hybrid fusion construction, the threshold increases to 10%. And additionally, because I'm now only creating these Z errors which have defects in horizontal planes, I don't need the vertical dimension of my cluster state to the same degree. And I can use flattened cluster states that use fewer qubits. Additionally, because I'm using a measurement-based error correction protocol, I am measuring out each qubit after a shallow number of gates applied to it. And so I don't need atom replacement mid-circuit either, which is nice to implement experimentally. Finally, if we discover a hypothetical qubit that experiences 100% biased erasures, we would have a platform which experiences a gate-level error threshold of 18%, which would be also great to have an experiment. With that, I come to the end of my talk. I have shown you why this error model, biased erasures, experienced by the metastable ytterbium atom is interesting. It has high thresholds when used in error correction codes. And by studying this error model more closely, we came up with this hybrid fusion protocol that further increases the threshold and reduces qubit overhead. There's a lot of current and future work that can be done in this direction. One of them is in Jeff Thompson's group at Princeton, where they have achieved an erasure fraction of 33% in an experiment. Future work can include exploring biased erasures on other platforms and seeing how the sub-threshold scaling actually is in realistic error percentages. With that, I come to the end of my talk. Thank you.
Thank you very much.
Great. So you did this very nice detailed study for the XZX surface code. Can you just comment, was there really any reason to use that XZX and not just CSS?
That's a very good question. So let me go back to this slide. So over here, what we saw, it was kind of an unexpected result for us that we still got an improvement for biased erasures in the XZX surface code in the absence of this bias preservation. The reason we got this improved result was what arose from what we call a reduction in noise entropy. So you know that you've got a Z error, or if the erasure occurred at a control Z gate, or you know that you've got a possible X error if the erasure occurred after a control NOT gate. So really, there's no difference here for the gate-based approach if you use an XZX surface code or regular CSS surface code, because you have the same kind of noise and entropy in both cases. In the fusion scheme, it does make a difference. Our XZX cluster state construction does ensure that you have these bias preserving error channels.
Any other questions? Well, okay, just so this also applies to like however long your circuit is. So is there a different scaling with depth of your circuit, or it's just kind of?
No, there's no difference in scaling on depth of the circuit. One good thing about the cluster state is that it looks like you're going to need a cluster state that scales linearly with the depth of your circuit with using that many qubits, like order d qubits with depth of your circuit. But in fact, you can use a cluster state that uses only order 2 qubits by teleporting information back and forth between the first 2 layers from the left of the cluster state. So in that sense, your scaling is similar to the surface code approach for the cluster state.
Okay. Yeah. Okay. If there are no further questions, then let's thank Kaavya again and.